All right, so now we're going to talk about hurricanes themselves. So remember that a hurricane forms from a tropical storm, which in turn forms from a tropical depression, and a tropical depression from a tropical disturbance. All right, so a hurricane, once it is formed, it averages somewhere about 500 to 600 kilometers in diameter. So remember, as I said in the beginning of this lecture, that Superstorm Sandy was, before it became a Superstorm Sandy, it was a hurricane in the ocean, and it was 1,800 kilometers in diameter. So very, very large. Okay, so if they're going to be in the northern hemisphere, these hurricanes, they're going to be rotating counterclockwise towards the center. And if they are in the southern hemisphere, they're going to be rotating clockwise. So mature hurricanes are going to be traveling in a forward speed about 19 to 27 kilometers per hour, meaning if the hurricane is happening in Boise, which is again almost incredibly unlikely as anything, it's going to basically travel through Boise and Meridian and whatnot and hit Nampa in about an hour or so. So that's how fast it's moving, okay? All right. So the wind speeds of the hurricane, as we saw, for it to be called a hurricane, need to exceed 119 kilometers per hour. However, those speeds of 119 kilometers per hour or higher need only to be within the innermost 160 kilometers of the hurricane itself. So again, because a hurricane is on average 500 kilometers in diameter, the inner 160 is about this much that I'm kind of pointing out. That diameter over 160 has to maintain the speeds of 119 kilometers per hour. However, the outer layers, if you would, of that hurricane forming don't have to be nearly as fast. In fact, the outer part of hurricanes, for the most part, has a speed, or wind speeds tend to be 50 kilometers per hour usually. Okay? Alrighty. So these rain bands, as you're seeing in the diagram, I don't know where my arrow is just looking so funny. These rain bands, as you're seeing in the diagram, are these kind of spiraling clouds that tend to form how we see hurricanes on a satellite image, right? So they're going to form this cloud areas that are going to be kind of subdivided from the next rain band by an area that is not having as much precipitation. Okay? All right. So the innermost part is going to be called the eye. Where is it? The eye over here. The eye, for the most part, has very low wind speeds, and it also doesn't have any cloud formation. So it's a really passive area. However, anywhere next to the eye is called the eye wall, and the eye wall is where you're going to get the most amount of possible damage. So you have the greatest rain that is falling, the greatest amount of rain, and also the greatest wind speeds. So in the eye wall, you have, again, highest wind speeds, and the average rainfall that happens in the eye wall is about 250 millimeters per hour. So that means about 10 inches per hour of rainfall in that particular area of the rain wall. So that is a lot. So if we go back to our scenario of the hurricane happening in Boise and moving towards Nampa, that means that in 1 hour, we're going to see 10 inches of rain, throughout the valley from Boise to Nampa, not even throughout the whole valley, but just in that small area, 10 inches in 1 hour. So very high amount of precipitation just for the eye wall. And obviously, you're also going to get a lot of precipitation from the rain bands that are adjacent to it as well. Okay, so when we have these changes in the hurricane, those changes have to be, or they're going to be very important for prediction of what's going to happen to the communities affected by the hurricanes themselves. So meteorologists put a lot of effort into predicting the changes happening to a hurricane or a tropical storm. So recently, actually, they discovered that very tall clouds, up to 12 kilometers high, actually form within the eye wall 6 hours before the storm intensifies. So these tall clouds are called hot towers, and they're called hot towers usually because you have, moisture air that is developing. It's unstable as it's becoming cooler and cooler and condensing. So you have this very kind of tall clouds emerging out of the air of the eye wall, kind of like how I'm pointing out here. They would look kind of like that. And if we're able to see them, say with, for example, Doppler radar strategies, then we are able to warn the community that, within 6 hours, if the hurricane is occurring, the storm is going to intensify, if anything. So you're going to get even more rain than you are at this point, for example. So the outflow of this warm air, as you're seeing in the image, is actually a pretty important mechanism for the transfer of heat from the Earth's tropics to the polar regions, right? So the air that was warm, that was initially intaken from the low surface of the air ocean waters, is going to travel through the hurricane and eventually is going to outflow here at the top. But because it stays within the hurricane for such a long time, and the hurricane itself is moving westward and northward, then overall the outflow is later on gonna, go towards the polar regions overall. Not necessarily in the poles, but more northernly and more southerly than where it was, initially kind of intaken, if you would, by the hurricane. So that means that this transfer of heat from the tropics to the polar regions, it's a very cool mechanism that is used, or hurricanes are a cool mechanism used to transfer this heat. So also, as I was saying before, the movement of the hurricane is controlled by the Coriolis effect, right? So it deflects the storm to the right in the northern hemisphere. And that means that usually the track that the hurricane's take is going to be westward in the Atlantic Ocean, and then later it deviates towards the north. So it moves fairly slow overall at forward speed. So again, 19 to 27 kilometers per hour. I mean, that seems slow when you're looking at it on a satellite image in the ocean. Obviously, if you're in land, it feels incredibly fast as it's hitting you, if you would. But because of that speed, that means that communities usually are affected by these hurricanes about 2 days or so, depending again, obviously, on the size of the community and also the speed of the hurricane. If the hurricane is moving a little bit slower, then perhaps they're only gonna, they're gonna experience the effects more than 1 or 2 days, perhaps even 3. But if it's moving fairly fast in a forward speed, then they might only encounter the effects of it for 1 or maybe 2 days instead of 3. Also, towards the end of the life of a hurricane, the speeds at which it's going at, not the inner wind speeds, but the forward speeds at which it's going at, tend to increase. So they can go all the way up to like 75 to 95 kilometers per hour towards the end of its life. So although at this time you're probably going to have less inner wind speeds and a little bit less rainfall, the overall forward speed may cause the hurricane to affect a lot of communities, and it becomes a little bit erratic at this point. Kind of like how we saw the tornadoes become erratic towards the end of their lives. Same thing happens, but obviously on a major scale for these hurricanes. However, once they reach this kind of end of its life, they tend to dissipate, and this tends to happen at least here in the North America Atlantic area. This tends to happen in the northern Atlantic waters, which tend to be a little bit cooler. So usually past that area, you're no longer going to see hurricane formation or development. So we just saw tropical cyclones. Now we're going to go over extratropical cyclones. So 2 main ingredients are needed for these extratropical cyclones to occur. You need a strong temperature gradient in the air near the surface. So that means usually you need either a cold, a warm front, or a stationary front. So most of these extratropical cyclones develop along these types of fronts. Okay, so those things are needed. You also need the wind patterns within the jet stream. What that means is that the jet stream will usually curve and bend north and south of their usual trend, as you're seeing kind of in the picture over here, and usually along these areas of high and low pressure, right? That's why they actually curve. So the cyclones themselves are going to tend to develop in these areas of bending, usually on the east side of the troughs. Okay, so again, the troughs are going to be areas of low pressure. On the east side of the troughs is usually where you're going to get these extratropical cyclone development undergoing. And again, it usually happens when you have a wind pattern within the jet stream itself. So the jet stream is going to be very high wind speeds, and once they pass through an area of low atmospheric pressure, you're going to get the formation of these extratropical cyclones. So a few examples are the Pineapple Express. So the Pineapple Express is one of the extratropical cyclone kind of patterns that are seen. So it's a series of extratropical cyclones that develops during some winters in the Pacific coast. So they usually track northeastward, I guess, and they kind of originate near Hawaii, which is why they are called the Pineapple Express. Another example is going to be the nor'easters. So we talked about the nor'easters a little bit in the last chapter. So they're going to be forming in the southeastern US for the most part, and they're going to track along the eastern coast, basically going northwards, which is why they're called nor'easters. So these extratropical cyclones tend to intensify when crossing areas of low-level temperature gradients. So that's kind of weird to think about, but a good example would be that when one of them is crossing the western US, they are losing speed when they cross the Rocky Mountains, and then once they cross the Rocky Mountains, they're going to pick up speed as they get into the Great Plains. So living in Bozeman, Montana, you could also see this pretty well. So Bozeman, Montana tends to be kind of like one of the most, I guess, eastern edges of the Rockies. And if you drove just a little bit further east, you could see this occurring a lot. So once you passed the mountains, the wind speeds picked up immensely. So in these areas is where you get intensification of these extratropical cyclones, for example. So let's see. They usually form in the mid-latitudes within bands of the westerly winds. Sorry. So they're coming from the west, going east for the most part. So they track eastward within North America. That's why they come from westerly winds. Okay. So predicting the formation and the transition of these extratropical cyclones is pretty complicated overall. And the strengthening of one of the reasons for this is that because the strengthening of them can happen as fast as 12 to 24 hours, margin. So that's pretty fast. And they're also steered by winds in the middle of the troposphere at around 5,600 meters. So these winds in the troposphere, sometimes being the actual jet streams themselves, tend to be the ones that kind of, hurry this extratropical cyclones a lot. They make them actually continue to go on eastward. So overall, the forward movement of the extratropical cyclones from west to east is generally half the speed of the steering winds. So if the winds that are steering my extratropical cyclone, again at the altitudes of 5,600 meters, are say 100 kilometers per hour, then usually the speed forward of my extratropical cyclone is about 50 kilometers per hour. So that's actually not insanely fast given the track of these things, but it is somewhat fast overall. Okay, so again, the forward speed of the extratropical cyclone is going to be about half the speed of the steering wind up above.